Hello, welcome to 7.1. Today we're going to be doing nth roots and rational exponents. So some of this is going to feel familiar, some of this is new, you haven't seen this before. But we're going to start out with just a quick little review of what exponents do here. So note we have 6 squared is equal to, we know that that's just 6 times 6, so we would get 36 for our answer. Now notice the difference here on these next two. We have a negative 5 in parentheses, and then we have negative 9 squared. So the difference is, when you have it in parentheses, the square is affecting everything inside of the parentheses. So this is actually the same as negative 5 times negative 5, or you can put them in their own parentheses. We know two negatives would make a positive, giving us 25. The tricky part here on this next one is this is actually negative 9, and then it's 9 times 9. That's what's happening first, is it's squaring the 9. The negative is like having a negative in front of the parentheses in this instance. So the answer here is going to stay negative. It becomes negative 81. So just make sure to note the difference on these. If you square in the parentheses, you're going to end with a positive. If the negative is outside, you can end with a negative, depending on what you're squaring. Now we're going to look at radicals. This is some important vocabulary that we're going to talk about, especially the word index. That indicates what type of root you're taking. So if you're taking the square root, we actually assume that there is a number there. It's like a 2. If you see a plain old square root, you can assume that it's a 2 there because you're looking for groups of 2 or pairs. Now when you're taking a cubed root, like what we see here, you're looking for groups of 3. Unfortunately, 8 is a perfect cubed root because it breaks down. If we do the factor tree method, we can get 4 and 2, and then 2 and 2, giving us a whole group of 3. So we know that our answer is going to end up being 2 because that one group makes out 2. Some other vocabulary to note here is the radicand. That is the number inside, or the term. There can be multiple pieces to it. It doesn't have to just be the number. And then we have the radical symbol. That's that square root looking symbol that we're used to and we've seen in many situations. All right, we're going to look at a few on this next part. So here we're taking the square root of all of these problems. Let's look at the square roots in a little more detail. So when you're taking the square root of 25, we could do this one without breaking it down. We instantly assume that the answer is 5 because we've done it, a lot of times. But we can also break it down. We know that 25 divides into 5 times 5. And the reason that it's exactly 5 is because we have a pair here. We have a group of 2 because that would be our index. We would assume that there's like a 2 in front of the square root. Now here's where it gets a little tougher. If you recall, if you try to type in the square root of negative 25, we've learned in Algebra 2 that that's not a real answer. We would get an imaginary solution for this. For this particular unit though, we're going to be focusing on real answers. We're not going to want any imaginary solutions. So we can assume that this one is actually going to be no real solution, if you want to write that. So if it ends in a square root, taking the square root of a negative number, you can write no real solution rather than writing 5i for this unit. Okay, 90 is not a perfect square root, but it does have factors that are perfect squares. So this is another way you can approach these problems. If you know that a perfect square would multiply to make a number, such as 9 and 10 in this instance, we know that 9 is a perfect square, so this is an alternate method you could use. You can take the square root of 9 and the square root of 10 separately. We know the square root of 9 is 3, it comes out perfectly, but the square root of 10 is not a perfect square, so that would just end up staying as is. This would be the simplified exact answer that I'm looking for in this unit. The next one, similar idea here. You don't have to do that method where you multiply by perfect squares because 75 has multiple factors. So let's say we wanted to do, 5 and 15. The reason I chose that is because neither of those are perfect squares. So you can do this method where you do 15, you break that down into 5 and 3, and here's our pair of 5s. So we know that 5 can stay on the outside, but we're left with this lone 3 since it doesn't have a partner. That's why it stays inside of the square root. This is the exact answer that's simplified down. Okay, now we're going to introduce some variables in this next situation. So here, 16 is a perfect square. That's great. We know that the square root of 16 is 4 and 4, so we can pull that out. Now, a to the third power. we can think of this in terms of factors as well. We know that one way to get a to the third is a squared times a single a. And then a squared, that's a perfect square. So that'll break down into a times a. So here is a group of a's. We can pull that on the outside. I'm actually going to move this down just a little bit. And now we've accounted for the 4's, the a's, but we do still have this lone a that didn't get pulled out. So that's going to stay inside of the square root as a single a. So this is our final answer, 4a times the square root of a. That's the reduced or simplified version of that radical. Okay, let's try this next one here. I'm going to show you another way we can do this as well. So 20 can break into 4 and 5. 4 breaks into 2 and 2 because it's a perfect square. So we got a group of 2's. If I assume that this is a 2, this is my index, this is another way you can think about how to break up variables specifically. If you look at x squared, we know that we can take out 2 x's or a group of x's, and that's going to come out as a single x. You can also think of it by taking 2 divided by 2. Your exponent divided by the index, we would get 1. So that means that we can take out exactly a 1. All right, because I did 2 divided by 2. Now if I do the y values, I could take 5 divided by 2, and that is 2 with a remainder of 1. So what that means is I can pull out 2 groups of y, or in our case y squared, and then what I would have left inside, I still have this 5, don't forget about the number, and then I had 1 extra y that I couldn't pull out, so that y is going to stay here. Just to show you this one more time to help you clarify. I could think of this as y squared and y cubed, and then let me break down y squared one more time. Y squared and y. So I would have a y squared, a y squared. Each of those would come out as y squared on the outside, but this y squared is what stays inside. But this is your final answer here. Okay. Give you a second if you want to pause that and write that down. All right, now we're moving on to cubed roots. We are going to get to some higher degrees here, cubed roots, fourth roots, maybe even fifth roots in some examples. Now we're stepping away from the square roots and we're looking for groups of 3. That's what our index is telling us. So when it comes to numbers like 80, it is quick if you recognize perfect cubes, like what we've done in the past. So we know that 8 and 10 are multiples of 80. So if you take the cubed root of 8 and the cubed root of 10, we just did the cubed root of 8 earlier. That would break up into 2. And then the cubed root of 10, that's not a perfect cube. So then we could leave our answer like this. Here's a quick list of perfect cubes, just in case you want to write this down. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. And you might see other ones bigger than this, but that's just a quick little list if you want to jot that down, because if you recognize those numbers, you can break it down pretty quickly. Okay, so here's our next one. We got 81, and 81 maybe isn't as evident what it should be. So I'm going to break this down here. I'm going to write that as 9 and 9, and then I'm going to write this as 3 and 3, 3 and 3. And again, I'm looking for groups of 3. Maybe I should change my color here once in a while. So that means I can take out a group of 3. They come out as a single 3. And then I'm going to be left with a 3 inside. This one's got to go down here. Okay, now I have p to the 5th, which means I can at least get one group. If I break down p to the 5th, I could think of that as p to the 3rd times p squared. Whenever you have a power of 3, that's perfect, because that comes out as a single group of p. So then I can write this as p on the outside, because the cubed root undoes a perfect cube. And then I would still have p squared left inside. And then lastly, I have m to the 3rd. If you wanted to, you could break that up into m squared and m, and here's a group of m's. However you want to look at it, but I know that I have to take out one group of m's, and that's going to come on the outside. So then this would be our final answer. All right. Now, as soon as we see a negative here on this next one, we're probably thinking, oh, dang, we're probably going to get an imaginary solution. The thing is, notice we have a cubed root rather than the square root, when it comes to powers of negative numbers, they come in even or odd pairs. So when it's even, when you're trying to take the square root or even the fourth root, like an even root of negatives, it's never going to work because there's never two numbers that multiply to make a negative. But there are three numbers that could multiply and make a negative. So for example, we're going to see here, 125 can break up into 25 and 5. And then this can also break up into 5, 5, and 5. So if we assume that every single one of these 5s is actually a negative, then we can get our answer. All is the same. It would come out as just negative 5. Because three groups of negatives will stay negative when you multiply them. Now we just did this exact same one, but it's positive 125. So that just means that our answer is going to come out as positive 5. You don't even need to break that down if you just remember that number. Okay, on to the fourth roots. Back to the even roots. So now, like we were doing before, we are going to assume that these come in groups of 4. So 64, I'm going to do 8 and 8. Break this down. I'm going to do 4 and 2, 4 and 2, whatever method you like to do best. 2, 2, 2, 2. Okay, so now I'm looking for groups of 2, or excuse me, groups of 4. So I'm going to circle 4 at a time here. So that single group is going to stay on the outside as 1, 2. And then what I have left inside are these two here. These 2's are going to multiply back together. Note I said multiply. It's easy to forget it because 2 plus 2 is the same as 2 times 2. But in this case, they're going to make a 4. 4 is what stays inside. So then our answer is 2 times the fourth root of 4. Continuing on here, we have the fourth root of 80 x to the fifth y to the eighth. So in this case, I'm going to break it down. I'm going to start with the 80. Let's go like 8 and 10. 8 breaks up into 4 and 2, 2 and 2. 10 breaks up into 2 and 5. And the reason I chose that is because now I can see 4 of a kind here. Those are all going to come out as a single 2. But I'm going to be left with this 5 inside. Okay. Now, thinking about this, 4, I can take out a whole group if I break x to the fifth into x to the fourth and x, because those would multiply to make x to the fifth. So taking the fourth root of x to the fourth will just leave me with a single group of x's on the outside. This, however, I'm going to circle these ones in red here, they got to stay inside. When I do the next one, though, y to the eighth, that's the same as y to the fourth times y to the fourth. And that's a group of 4 and another group of 4. So since I have two groups, those are going to come out as y squared. Okay. You could also think of it as 8 divided by 4 is 2. So that's the number of y groups you can pull out, 2 groups of 4. And then we're still left with those pieces on the inside, so don't forget about that 5 and that x. And I also want to try to remember to write my index. It's not the end of the world, but you do want to remember you were taking the fourth root. The fourth root is technically different than the square root, so try to remember that for your final answer. Okay, now we're getting into that situation where it's just a plain number. Hopefully this one breaks down perfectly. 81 breaks into 9 and 9, 3 and 3, 3 and 3. Boom. Perfect group of 3. So we get just an answer of 3. That whole thing, the fourth root of 81 is 3. So that's our final answer. This one, however, notice it's a 4, and we have the square root of the fourth root of negative 81. So just to show you why we can't get negative 3 for an answer, if I assume that this was like negative, well, let's just assume that this would break into 4 parts, all negative 3's. If I try to multiply those out, these two would become positive 9, these two would become positive 9, this would come back to 81. Since we can't get back to the negative version, that's why this is an invalid logic here. You have to assume that there's no real solution because you can't multiply 4 of the same number and get a negative answer. So this one would be another no real solution. We know there's a solution. It has to do with the imaginary numbers, but in this case, we don't want those. We only want the real solutions. All right, now this is the part that's a little bit more new. You haven't seen this before. But we can write square roots with rational exponents. The way that you do this is it's the power of your radicand divided by the index. So a to the x over n. X is the exponent. I'll just write that here. Exponent of your radicand over the index. So whatever the number on the outside of the square root or the radical sign, excuse me, if it's a square root, you know that your index is 2. If it's a cube root, the index is 3, and so forth. So now we're going to practice rewriting this. This is going to be a big component of the homework as well. So if we assume that the power of 5 right now is a 1, then we can rewrite our answer here as 5 to the 1/3 power, because 1's the exponent, 3 is the index. Okay, these ones are a little tricky, but remember that we assume there's a 2 on the outside if it's a plain square root, and then we can assume that it's a power of 1, so this is 7 to the 1/2 power. This one would be 2, here's our exponent, so that goes on top. 3 is the index, so it's 2 to the 2/3 power. And this one, we would have 15 to the, here's our exponent, 7/4 power. I would suggest leaving these as improper fractions. You don't have to rewrite that as 1 3/4 power. I would just leave it like that. Okay. We can also go backwards, and that's what's really nice and going to be super powerful when you have an answer that looks kind of funny with a fractional exponent. Going back into the radical is typically going to let us simplify a lot easier. So I'm going to rewrite the expression here. So I know that I'm going to get a radical. I know that 3 is the number going inside. That's the radicand, or the base of the exponent. And then since it's 2 on the bottom, you don't have to write the 2 there. It's not wrong if you write it, though. It's still a square root. And you don't have to write the 1 because we instantly assume that this is actually a power of 1 if we don't see the number. So either of these is fine. Then we got 5 to the 2/3. So we could write that as the cubed root, because that's what's going here, of 5 squared if you want to write it like that. Or you could write it as the cubed root of 5, and then you could put it in parentheses like we saw up above. Knowing this idea is also important too. You can write it in either version of that. You could even write it as the cubed root of 25. That would be the same. But we're going to try to leave it with the exponent so we can visualize that for right now. Okay, this one would be the 4th root of 6. You don't have to write the 1. You can assume that it's 6 to the 1st power. And then this one would be the square root. You want to put the 2 there, that's fine. Of 8 to the 5th, or I'm going to rewrite this one as the square root of 8 to the 5th. Either way, either of those is good. You can do either or. Okay, now we're going to do some evaluating. I think this is the last part. Yeah, it's kind of a long lesson, but we'll get there. Evaluate without a calculator. So here, 625, I'm going to help you out. That's 25 and 25. This breaks up into 5 and 5, which means this is actually a perfect 4th root. It comes out to be 5. Here, hopefully we note right away it's an even index. We don't like even indexes when it comes to negatives because it won't break up. So this one would be a no real solution. All right, then we got the 4th root of 81. I think we did this one earlier. 9 and 9, 3 and 3. I apologize if I'm going through this one fast, but we've seen this before. This one's just 3. Now, this one, be extra cautious because we were just practicing the rewrite. We didn't see one where there was a negative number on the outside. So for this example, you can assume that this is actually the same as 81 to the 1/4. That 1/4 is not affecting the negative because the whole thing wasn't in parentheses. So we can actually rewrite this as negative, and then it would be the 4th root of positive 81. So then our final answer is -3. We don't violate anything here because the negative is on the outside of our square root or our radical. Then we can assume that it's fine. We would get +3 from the 4th root of 81, and then we would just throw the negative in front of it. So that's our final answer on this one. Okay, let's do a similar setup here on these next few. Notice this one's in parentheses this time, so we do have to include the negative in our radical. So since 3 is the index, it'd be the cubed root of -27. And this is where it's really important to note that we can put the 2 on the outside of our parentheses. The reason I'm doing that is because I know that I can take the cubed root of 27. That's a perfect cube. And then when I square it, that just makes it easier. So the cubed root of -27, if you recall, 27 is a perfect cube. It ends up just being 3. But because it's a -27, it's actually going to be -3. We're going to keep the parentheses, and -3 squared would end up being 9. Over here, we got -27 to the 2/3. So this time I'm going to do the exact same thing, except for the fact that the negative has to stay outside. So I'm going to put this in parentheses. It's the cubed root of 27 squared. But the squared is on the outside, the negative has to stay on the outside because it wasn't included with the rational exponent. So now it's going to be -3 squared. And you have to remember order of operations. Exponent comes before multiplication. Technically, this negative is like a -1 multiplying with it. So we have to do the exponent first, which would give us 9, and then it's -9 for the final answer. Okay. All right, lastly, we have these negative exponents. We haven't talked about this rule before, but you may have seen this in the past. A negative exponent just brings it to the opposite part. If you were to treat this like a fraction, what it does is it brings it to the bottom. So now it becomes 1/9, and then the exponent becomes positive. So it's 1/9 to the 3/2 power. Okay, and then 9 to the 3/2 power would be 1 over the square root of 9 cubed. It's a square root because 2 is on the bottom. And we know the square root of 9 is 3. So 3 cubed would be 27. So then our answer is 1/27. Notice that it did not make our answer negative just because we had a negative exponent. It just made it a fraction for our answer. Okay, over here, we're going to have a situation except we have a negative on the outside. So that part is going to affect it. So what this does, I'm going to keep the negative in front. I'm going to put a 1 over, and then I'm going to bring 32, and I'm going to rewrite this whole thing. Well, let me just write it first. Once it goes to the bottom, though, it becomes a positive. We're going to stress this a little bit more in the next lesson. You'll see what we do with the negatives. But now I'm going to rewrite it as a radical. So 1, and then it's the 5th root of 32. I'm going to keep this to the 3rd power. And we design these that you can do it without a calculator because you're going to have to do that for this test. But the 32 would break into, let's go 8 and 4, 2 and 2, 4 and 2, and then 2 and 2. So this whole thing is a group of 5 2's. So then that simplifies to 2 to the 3rd power, which is 1/8, or 1/8. Okay? And that is it for this part. The final thing is a couple solving problems, so I'm going to go through those quickly here, and then you can get started with whatever you need to. So whenever you're working with equations for real roots, this is kind of your goal. Isolate the power, take the appropriate root of both sides, that's the inverse operation, and then continue with the opposite operations if necessary. So just to remind you, if you had x squared equals 25, you would recall that you would have to take the square root of both sides because that undoes a square. So in this case of x to the 3rd equals 125, we're going to take the 3rd root of both sides because that's going to undo the cube that we have here next to x. So then those are inverses and we're just left with x equals, and the cubed root of 125 is 5. We did that earlier, so I'm just going to kind of jump to that conclusion. Next one over here, if I divide by 2, because I want to isolate, so I want to get that x cubed all alone, this would end up being negative 8. Once the x cubed is alone, take the inverse root of that, which is the cubed root, and we would get x equals negative 2. The reason it's negative 2 is because it's a negative 8. So you can assume your answer is going to be negative here. We don't have to worry about the plus or minus in this situation because it's an odd root. If it's an odd root, it's always just going to be that exact version. Either if you're taking cube root of a negative, it's going to stay negative. But when we get to the even parts, that's when we have to consider the plus or minus like we did before. Okay, here we've seen problems like this back when it was squared. So we do the inverse order of operations. We would add 3. We keep the 2 on the outside. Remember, do not distribute that 2. That would not be good. Negative 19 plus 3 is negative 16. Divide by 2. We get x plus 4 to the third equals negative 8. And it's very similar to the last one, except for the fact that we have a parentheses here. We can still take the cubed root. So then it becomes x plus 4 equals negative 2. And then you just have to remember to subtract 4. Our answer ends up being x equals negative 6. Last one here. This one we would add 7 to both sides. And this is going to work out perfectly. Most of the time the solving ones are going to work out pretty nicely. That becomes 10,000. If you take the fourth root, because we want to match the exponent in the index, we could break 10,000 into 100 times 100. That would break up into 10 and 10, 10 and 10, and there's our group right there. So we know that x would equal 10 in this instance, but because it's a fourth root and it's not a cubed root, that's an even number. This is the situation where we actually have to consider plus or minus. Because if you multiply positive 10 times itself, like 10 times 10 times 10, you would get 10,000. But if you do the negative version, that also would work out because all of those negatives would eventually become positive and you would get 10,000 as well. So that's why we have to include plus or minus only if your power is an even power and you take an even root. All right, that is it for this one.